in our model so far, we were only considering one feature for our modeling purposes. We were only looking at the percentage of population that are driving. And but we don't have to just use one feature when we're working with linear regression. We can include more than one feature for our model. In other words, use more than one feature to best fit some hyperplane through our data. And the reason why I say hyperplane is because if we only have one variable we're working with, as we saw before, we're trying to do is draw a line through our data. If we have two features, then we have a three-dimensional space. Two axes are x1 and x2 are two features, and the third one are the labels, the y, and we're trying to draw a plane through the points. At higher dimensions, that's a little harder to visualize. I can't do that. So instead of drawing a line or a plane, we're going to say hyperplane. So hyperplane is just a generalization of a line or a plane in some sort of higher dimensional space. So for this extended model, let's go ahead and look at the features we can play around with for our model. And we'll go ahead and have an interactive visualization. So one of the things you want to do when you're tackling a problem is, let's understand how our features relate to the value we're trying to predict. So let's plot them. Let's plot each feature against the value we're trying to predict. And we have to do it independently because it's easier to visualize one variable at a time. So this is how our gas consumption varies with gas tax. And if we look at it here, we see it's not too much of a strong correlation, but in general, as you increase the tax, gas consumption decreases. This is the percent of the population driving. We saw this before, and this was has perhaps the variable with the strongest linear correlation. So we expect that this variable is going to help us out the most to make a prediction, to make a correct prediction, a very accurate prediction for the gas consumption. Let's look at the other variables we have. We have the average income. Not a very strong correlation, but you see a negative correlation here. As the average income increases, generally the gas consumption decreases, although there are some notable outliers here that might cause some problems. Let's look at the last variable here, number of miles paved of highway. And here you initially have a strong linear correlation, but then something happens. And the miles of paved highway, even though you increase it, tends to correlate to lower gas consumption. So because of this really nonlinear behavior for this variable, it's probably not going to help us out a lot to predict gas consumption. So let's go ahead and extend our model here. So now we're saying is that our predictive value, the value we want to predict, is going to be equal to beta naught, the intercept plus the feature times a coefficient associated with that feature. So we still have that linear behavior. We're saying the predictive value, the value we're trying to predict, has a linear relationship with our features, scaled by a coefficient, this beta coefficient here. So notice all our four features have an associated beta coefficient with it. Let me just sketch it out right here. So in general, we can say y hat, what we're trying to predict, is beta naught plus beta 1 x of 1 plus beta 2 x of 2, and so forth to the number of features we have. So let's say we have p features. In more compact form, we can write this equation as if we use some matrix algebra notation. So I'm going to say these curly braces here represent a vector. And this is a vector of n number of rows. Right, so n by 1, it's a vector. So it's got one dimension, number of observations is going to refer to n. This is going to be equal to our feature matrix, n number of observations, p number of features. And we can collect these beta coefficients and represent it as a vector. So we have a vector of beta coefficients plus beta naught out here. More compact form. So we can go ahead and write this using summations. So this is writing out this matrix operation using summation operator. So the j index represents an observation, the I index represents a feature. You can sum them all up, and that's the equivalent form. So oftentimes you'll see it written out this way, but this gets a little annoying. Sometimes you'll see it written out using this notation here, or this more compact form where we use the summation sign. Sometimes people will do is called Einstein notation or index notation, where they'll go ahead and go ahead and omit the summation sign for any repeated indices. Sorry, this should be a summation with regards to, yes, summation of I. So since I is repeated on both variables, they can omit the summation sign. It's understood you're summing for that indice. I'll put y hat here to indicate that this is a predictive value. Okay. So now the question, our task is, well, what should be the beta coefficient values for each feature? Now let's go ahead and start visualizing some of our data. Let's try to visualize it in a two-dimensional space, or x1 and x2 to be yeah, x1 and x2 as our two features. So in this case, we have two features. We're only analyze two features. In this case, the tax and the percentage of drivers. Those are the two variables we looked around in our initial data analysis that perhaps has the most predictability for our gas consumption. That's a little harder to visualize, but our task now is not to draw a line through our data set, but to draw a plane through the data. So let's go ahead and use our linear regression model to fit with those two variables. And let's go ahead and visualize that plane. So this is our best plane to go through the data. And like I said, it's hard to visualize, but we can go ahead and take cross sections. That's what I'll do here. This interactive plot will allow you to inspect different cross sections of our plane with respect to changing the tax value. These are the corresponding cross sections. So notice here, since we're working in two dimensions, as I said before, we draw a plane through the data. Working with higher number of dimensions, we'll just call that a hyperplane. We'll see this concept of hyperplanes come back when we talk about support vector machines. Now obviously this was just done with two variables. Let's see what happens if we try to include all the four variables for our model. And other questions we want to ask ourselves is, from our four features, which one helped us out the most, or was the most important feature? Which one really drove the prediction for gas consumption? Because that's something we want to ask after we've trained a model. We can have a model to make predictions, but other things we want to know is, hey, which feature is most important? Which feature is really driving the predictive value? And we'll go ahead and see how we can do that with linear regression.